Hi there, everyone. Welcome to lecture notes for Chapter 4 for Stat 243 in the summer online. Notice that we don't cover Chapter 3, so if you're worried that you're missing lecture notes for Chapter 3, nothing to worry about. We go from Chapter 2 straight to Chapter 4. You can find the typed lecture notes in the Week 3 module, and obviously you found this video, which is also linked in the Week 3 module. Okay, so in this chapter, we're going to talk about discrete probability distributions. And so recall that a variable is numerical and discrete if the values of the observations are all numbers and they take specific values. Compare that to a continuous variable where the values can be any numbers in a range. So as an example, we could look at a discrete random variable is the number of games a team wins in a season. This can be 0, 1, 2, 3, etc., but cannot be 1.5 games. So in this chapter, we focus on discrete probability distributions. So the historical development of probability was or served the purpose of understanding gambling games. This is not my favorite use, but it is pretty common and it makes the mathematical understanding a little more relevant. So I'm probably going to stick with that for now. So let me give you an example of a discrete probability distribution. Suppose you flip a coin. If it lands on heads, you win $10. If it lands on tails, you win nothing. You win $0. How much money would you expect to win on average? This is the classic discrete probability distribution. It is a discrete random variable because the two values are 10 and 0. Right, those are numerical values. And they are the only possible values. Can't be $1, can't be $8.7. It's either 10 or 0. So to answer this question, how much money would you win on average? You need to know the probability of landing on heads and the amount of money you win on heads and the probability of landing on tails with the amount of money you win on tails. This lends itself very well to a table. So probability distributions of discrete random variables are almost always presented in tables. The distribution here is the range of possible values. The probability part here is the chance of getting those various outcomes. So here's our table for this example. We're going to have the outcome here, heads or tails. We're going to have the value of the outcome here. So $10 for heads, $0 for tails, and the probability of the outcome here. Well, if we're flipping a coin, it should be 50-50, and we represent it as a decimal. Almost always probabilities are represented as decimals, so the probability of getting a heads or tails is 0.5 for each. So this is a table representation of a discrete probability distribution. We can use this table to figure out how much money you would expect to win on average by extending the table a little bit in the following way. So let's copy the table. And add a column to the right. And we're going to do the value times the probability here. So we can build another column, which is the value times the probability. The value, if you land on heads, is 10. The probability is 0.5. And the value times the probability there is 5. I'm going to put dollar signs in to help keep track. And the value times the probability of landing on tails is $0 times 0.5, which is still $0. The average amount of money you would expect to win is the sum of all the value times probabilities. In this case, I'm going to write out the full calculation, 10 times 0.5 plus 0 times 0.5, which equals 5 plus 0, which equals $5. So on average, you would expect to win $5. But notice, okay, so this is an important piece of a probability distribution, is figuring out on average what you expect the value of this probability distribution to be. This average value is called the expected value of the probability distribution. It represents the average value of the distribution if you conducted a large number of trials and averaged out the winnings, I'll say the values of each trial. The notation for expected value of a random variable x is expected value of x and it's read the expected value of x. So in our example, the expected value of x is $5. A couple of things to keep in mind. In a probability distribution, the expected value, E of x, is exactly the same as the mean of the distribution. In the mean, like in the average sense. So when you ask what the average where the expected value of a distribution is, you're asking for the mean. A little bit of notation in statistics. We often use the Greek letter mu, which looks like that funny looking kind of an M, kind of a U. Mu looks like a mashup between an M and a U, which is kind of convenient because when I write mu in with English characters, I just write MU, and that's what everybody does. So because most of my notes are going to be typed, I'm usually going to be using the MU spelling as opposed to the Greek letter spelling. And same thing in R, I'm going to be using the MU spelling as opposed to the Greek letter spelling. Okay, let's do another example. Suppose you roll a dice or a single die, which is a singular of dice. If you roll a 1, you win, let's say $5. If you roll a 6, you win $20. But if you roll a 2, 3, 4, or 5, you lose $10. Let's not do $10. Let's say you lose $3. There we go. Let's build a probability distribution table. Let's insert a table. We're going to have 6 outcomes. Which are 1, 2, 3, 4, 5, or 6. The value, we got $5 for a 1, $20 for a 6, and losing $3 is negative $3 for a 2, a 3, a 4, or a 5. Now the probability, as long as it's a fair die, is going to be probability is going to be 1/6 for each of those, which is about 0.167. I don't want that fraction. Sometimes we use probabilities as fractions instead of as decimals. We almost never write them as percentages, although we might talk about them as percentages. So let's figure out the expected value of this game. First, I'm going to do this through simulation using R. Imagine playing this game 100 times. How much money do you think you will have or you will make on average after 100 trials? So let's hop over to R. So I'm going to build myself a probability distribution. I'm going to say the outcomes are going to be, the outcomes are not the roll of the die, the outcomes are the values. So it was $5. Oh, I don't want the dollar sign. $5, negative $3, negative $3, negative $3, negative $3, and $20. And the probabilities we saw were all 1/6. Oops. 4, 5, 6. Okay. Let's run both those pieces of code and take a look at them. So the possible values were winning $5, losing $3, or winning $20. And the probabilities for those different options are 1/6 each. So let's suppose we do this 100 times, and we're going to roll the dice. Each time we roll the dice, we're going to get an outcome. So this is code for simulating outcomes of a discrete probability distribution. We can have 100, we're going to run it 100 trials. Each time we run it, we're going to get one of our possible outcomes. Replace equals true means if we roll a number 1 the first time, we could roll a number 1 the second time as well. And our probabilities of getting those various ones are 1/6 each. So I'm going to run that. And here are all the possible, or here's one possible set of 100 trials. Won $20, lost $3, lost $3, lost $3, lost $3, won $5, won $20, lost $3, won $5, etc. So on average, we won, well, I would add all of those 20, all of these different values up. The sum of all the trials divided by the number of trials. Do you see how that's exactly the same as the definition of the average mean, where you add up all the outcomes, where you add up all your data and you divide by your number of observations? So let's do that. And in R, it's pretty simple. We can take our code and we can just take the mean of that sample. And we see that on average for this sample, we made $1.66. Let's do it again. This time we made $1.05. And again, this time we made $2.80. When you simulate your data, you're not going to get the same thing every time. So it can be hard to figure out from the simulation what your mean is. But there is a trick, and in fact, the most important strategy in statistics for improving the accuracy of your statistics. It's very simple. It is increase the sample size. If you remember anything from this course, it is to improve the accuracy of your statistics, increase your sample size. So instead of running just 100 trials, let's try running 1,000 trials and finding the average. That time it was 2.3. Aha, also close to 2.3. 2.1, 2.1, 1.7. That was a weird one. Think back to the previous lecture video. 1.7 is surprising because it doesn't look like the others. But as we run more samples, we see they seem to be staying pretty close to about 2, as opposed to when we had a smaller sample, there was more variability. So let's go ahead and increase our sample size even more. And now we're super stable. Sure looks like the average is very close to 2.15 or 2.2. So that's how we would simulate the outcomes of a discrete probability distribution. And I will put this code in the lecture notes. Okay. Now let's use mathematics to determine the exact expected value. Let me just say, based on these simulations, it appears that the expected value is close to about, what was it, 2.15 or 2.2. Okay, let's use mathematics to determine the exact expected value. So we're going to take our probability distribution and we're going to extend it. With the value times the probability. So $5 times 1/6, that's like 5/6. Negative $3/6. That's going to repeat a bunch of times. And $20/6. So let me figure out what that is. What's 5/6? It's about 0.833. That is 0.833. Negative 3/6 is negative 0.5. So that one at least was pretty easy. And 20/6 is 3.33. Okay. So the expected value, E of x, is going to be adding all of these different numbers. 0.833 minus 0.5, minus 0.5, minus 0.5, minus 0.5, plus 3.333. Let's see if R will do it. It won't, but that's okay. Drop it over into R. And we get 2.166. And it's $1 amount. All right. Well, notice that 2.166, the mathematical expected value, is very close to our estimate of the expected value based on simulations. Okay. All right. I'm going to close this video here. In the next video, I'm going to talk a little bit more about not just the mean of a discrete probability distribution, but also the variance, how much we expect those data to spread out when we do our trials and collect information. So I'll see you in a minute.